If you remember, an angle bisector divides an angle into two smaller congruent angles. And in this video, we are going to go over the angle bisector theorem. Here I have an angle. This is one side of the angle, and this is another side of the angle. So I'm going to draw the angle bisector. So if this new line is the angle bisector, then this angle is now congruent to this angle. And what this theorem says is that if I have a point anywhere on this angle bisector, let's say right here, and let's name this point P, then it is equidistant from the sides of the angles. And remember, to find the distance between a point and a line, you draw a perpendicular line branching out from that side to a point. So my perpendicular line would come out from the side, and my other perpendicular line would come out from the other side of the angle. And this theorem says that the distance from one side to the point P is congruent to the distance from the other side to the point P. We also have the converse of the angle bisector theorem. The converse of the angle bisector theorem, T31, says that if we have a point in the interior of an angle and it is equidistant from the sides of the angle, then it is on the angle bisector. That's saying if we didn't know that point P fell on the angle bisector, from this theorem, as long as it is the same distance from one side of the angle to the other side of the angle, then it does lie on the bisector of the angle. Let's go ahead and prove the angle bisector theorem, T30. Let's go ahead and do an informal proof. We're given that AX is an angle bisector. So AX bisects angle BAC, and the segment XR is perpendicular to the ray AB, and the segment XS is perpendicular to the ray AC. And we know that because AX is a bisector, then angle XAR and angle XAS are congruent. We also know that AX is congruent to AX, and that's by the reflexive property. Now we're trying to use one of our congruence postulates to say that the measure of XR is the same as the measure of XS. So far that we have corresponding angles are congruent and a corresponding side of two triangles is congruent. But since these are perpendicular, we know that they're right angles and are 90 degrees. And 90 degrees is congruent to 90 degrees. Therefore, we have another angle that is also congruent. Angle ARX and angle ASX are right angles by the definition of perpendicular, so angle ARX is congruent to angle ASX because all right angles are congruent, and we know that to be true. Now you can see we have angle, angle, side, angle, angle, side. And the angles inside are both corresponding. So by AAS, triangle ARX is congruent to triangle ASX. And we know that if two triangles are congruent by CPCTC, corresponding parts of congruent triangles are congruent, then side XS is congruent to side XR. By CPCTC, the segment XR is congruent to the segment XS. Therefore, the distance x to r is equal to the distance XS. And that's by the definition of congruence. Since they're congruent segments, they're also the same measure. And that is what we needed to prove. Given a point on the angle bisector, in this case our point was x, then it is equidistant from the sides of the angle. The measure of XR is the same as the measure XS. Now, just as perpendicular bisectors in a triangle are concurrent, angle bisectors are also concurrent. The point of concurrency for a perpendicular bisector we learned in the last video is called the circumcenter. The point of concurrency for an angle bisector is known as the incenter. So incenter is the point of concurrency for angle bisectors within a triangle. In the triangle I've drawn here, the red lines are the angle bisectors, so this point is the incenter of the triangle. And just like there's a circumcenter theorem, there's an incenter theorem. The incenter theorem, T32, says the incenter of a triangle is equidistant from each side of the triangle. Remember, when calculating distance between a point and a line, it is the perpendicular segment that we're measuring between that point and line. So that means that this line is congruent to this line, which is congruent to this line. The incenter is equidistant from each side of the triangle. And to prove this theorem, remember, for the circumcenter theorem, you used the perpendicular bisector theorem. For the incenter theorem, you would use the angle bisector theorem.